Webinar. My name is Eric Ostergaard. I am an application engineer with HBM Encode and will be the presenter of today's webinar session titled Advances in Finite Element-Based Vibration Fatigue Analysis. The agenda today goes as follows. We're going to take a brief look into some of the functionality that we've had available to us in Design Life up until version 11. Then we're going to take a look at some of the enhancements that we have put into this year's version. Those are going to include the ability to do multiple PSD vibration fatigue. That's also going to include a demonstration. I'll show you guys another demonstration. We'll talk a little bit about some of the features in Sign-on Random. And then lastly, we'll do a section on modal-based vibration fatigue, which will also be followed by a demonstration and then wrapping things up with a conclusion at the end. So just to recap, for those of you who may not be as familiar with vibration fatigue products in Design Life, what it essentially does is allows you to simulate a vibration fatigue test. This can be driven by random PSD or swept sign loading, which are pretty common types of loading or ways to describe our loading. The finite element model will be represented with a frequency response function. And we have a couple of options where we would be able to include a static offset. This might be something that would be simulating bolt tightening, assembly loads, gravitational effects, and those would then be superimposed on top of the cyclic loads, which are caused by the vibrations. And we also have the ability to build duty cycles. So we can have essentially multiple events describing different types of vibration events that would then happen sequentially, and we can put repeats on any of those events inside the duty cycle to describe the duration of each one of those individual events. As you can see in the screen below, we have in the middle a box which essentially represents what Design Life is going to do virtually in terms of doing a virtual shaker table. We're going to provide at a minimum 3 inputs. Those main inputs are going to be the frequency response that you've solved for in FE. We accept a wide range of different solutions from FE codes. You're going to be describing the loading environment. In this particular screen capture, we've got a PSD, which would be oftentimes in the units of G squared per hertz or something fairly similar to that. And then we're going to describe the fatigue properties. Fatigue properties, in this case, being a stress life-based model. And from that, we're going to be able to generate damage results as well as some statistical results that we would get out of the vibration fatigue analysis. So some new things in version 11. Let's take a look at some of these. We have quite a few new loading methods. These include multiple PSDs, sign-on random, and sign-dwell. We've added functionality where we can also do modal superposition in the frequency domain. This can have huge benefits when we start dealing with very large models. We can much more efficiently manage modal stresses and then the modal participations, many times taking far less disk space than if we had done the frequency response function entirely in FE, solving from many frequencies. We also now have the ability to do isothermal analysis. So in addition to being able to add static offsets, and these, by the way, are now scalable, we can also add scalable temperature load cases. So if you have material properties where you've described different fatigue properties at different temperatures, and you have a scenario where you have thermal conditions, we can take that into account and apply the appropriate material properties there. Sorry guys for the pause there. I was just making sure everybody had the audio capabilities enabled. Getting back to the bullet items here, we have a couple of additional stress combination methods. We can do sine von Mises, and we have now the ability to bring all of the metadata that we may be describing in the vibration generator all the way into the analysis property. This wasn't always the case before, where we had to, unfortunately, describe things, the same information in a couple of different locations in a process. That's now been addressed with the capability of making use of the metadata. In the FE display glyph, we can now display magnitude, phase, real, and imaginary results. And we also have a new interface for the load mapping, which we'll see in just a bit. So let's take a look first at the multi-PSDs. All right, for multi-PSDs, it says 3 axes sequentially here, but it doesn't have to be 3. It really means just more than one. In the past, the capability that we had available to us, if we wanted to do multiple axes, was to do them sequentially, essentially doing one at a time, and really just building a duty cycle that would excite, in this example here, the X, then the Y, and then followed by the Z. Really doing exactly what a single axis shaker table could do physically, where we might position, reposition the parts to address the different axes. What we now have the capability of doing is exciting all 3 of these axes simultaneously. And this would be more realistic in terms of what a part might see out in application or out in the field. You can imagine, like in the screen capture right here, we might have some underhood components, some electronics, for example, mounted on a bracket on or near the engine. That is going to be excited in all 3 directions simultaneously, not sequentially, and having the capability to do this virtually is going to be far more realistic in terms of describing the type of durability issues that particular component might have out in the real world. So let's talk a little bit about what is in the load history. If we start first with some time series data, we have 4 main characteristics in that time signal. The first one is amplitude, and this is going to be very critical for doing any kind of fatigue analysis. It's essentially what allows you to describe how big a stress cycle or a load cycle is going to be, which ultimately translates into some type of a damage result. We have frequency as a characteristic as well, and this one is kind of interesting in that it is only important in dynamic analysis when we have a structure that we expect is going to resonate because of the vibration loads that are being applied to it. We have phase. This one really only becomes important if we have more than one load. If we just have one single load, we don't really have to describe how it relates to other things, and therefore phase isn't as big of an issue, but getting into multi-PSDs, it does become very important. And then lastly, we have cycle sequence, which can have an effect on fatigue. So when we convert things to the frequency domain, when we convert time series data to the frequency domain, we often make use of a Fourier transform, where we can describe a time signal with a series of sine waves. In this particular example right here, it's fairly discrete, where we've taken a time history and then represented it with just a series of 4 sine waves, each one of these sine waves having a unique amplitude and a unique frequency. Oftentimes plotting that on a plot that would allow us to display amplitude or power versus frequency. And perhaps maybe we can reconstruct that time series data if need be from the information described in the PSD, overlaying more and more of these decomposed sine waves to get pretty close, pretty good approximation of the original time series data. So again, just as a reminder, this works really well, and this is really all we need to do if we have a single load case or a single load PSD. It becomes a bit more complicated when we have multiple events, and we're going to see a couple of examples here when this importance really starts to show. If we look at a really simple example of a couple of flags on a flagpole, both of them being fairly close to one another, fairly high up on the flagpole, we might be able to say that the events being wind conditions on each of the flag, could be fully correlated if they really are in fact seeing the same type of conditions. If we look at the second example on the lower part of the screen, where we have two flags again, but one of them has been lowered, the lower of the two, it might be that it's starting to get into the boundary layer caused by wind conditions closer to the ground. That event is going to start to look a little bit more different than the event that we have closer to the top of the flagpole. And now we're getting into a scenario where we don't have complete correlation between those events. We would say that they're partially correlated, or there's definitely some similarity between the time signals, but they're not exactly alike. We can look at it another way as well. If we have two flags on two separate flagpoles spaced some distance apart, they would be partially correlated, primarily because there'd be some type of a phase shift. You have some event that occurs on the leftmost flagpole, and then moments later that same event occurs on the next flagpole. Or we could have no correlation at all. If we've spaced those two flagpoles far enough apart, or if one of those was much lower on the second flagpole, the time histories that we're going to see are going to be completely different. And we need to be able to describe how well these correlate. And that's what we're going to be seeing in this next particular slide. So just to recap, if we are fortunate enough where we only have one load PSD, what we can do is, if we are starting with time series data, do a Fourier transform, describe our loading in terms of something like g squared per hertz, and we can see we've got a sample plot right here. We're going to apply this load PSD to our frequency response function, one that we've solved for in FE with unit excitation across all frequencies. And by applying this load PSD to the frequency response function here, we can generate a local response PSD for each element on that structure. So now we end up getting a plot for each element that is going to be some type of stress PSD. We're going to have stress as a function of frequency, and then we can make use of counting algorithms such as Lalande or Dirichlet to determine the cyclic content within this stress PSD, and then we can use Miner's rule to determine how much damage is caused. Now, if we have two loads, or two load PSDs, there is going to be a relationship between these two. How well are they correlating? Kind of like what we saw in those previous slides. To describe this correlation, we also need to have a cross spectra and phase. This is going to help us to determine at a given frequency how much is one load PSD being excited and how much is the other one in terms of gain with respect to that one, and what is the phase? Are they together, or is there a little bit of a lag? With these two load PSDs and the cross spectra, we can come up with a stress PSD on each of the elements in the frequency response function. And once we have this stress PSD, again, it's just going to be a matter of using a cycle counting algorithm to determine the cyclic content here, and we can do our fatigue calculations. But the complexity definitely is in combining these multiple load PSDs together. Within ENCODE, the PSDs can be easily created with a frequency spectrum glyph. We can see that right here, and we're going to see a demonstration of this in just a moment. And the frequency response glyph right here is what will allow us to create the cross spectra and the phase plots. So let me go ahead and open up ENCODE for you. And what I'm going to do is I'm going to open up a standard flow. This is something that's going to be available to all users. And what it will do is create the PSDs necessary, as well as the cross spectra with phase. And it creates one more file, which really serves as a lookup file. It's a text-based file, fairly easy to read. That becomes really helpful. It's a nice user feature when we get ready to do fatigue calculations in design life with these PSDs and these cross spectrums. Let's go ahead and navigate over to ENCODE. And hopefully everybody has the ability to see this ENCODE session. If not, go ahead and just send me a message and I will double check that. And what I'm going to do is I've already navigated to a directory that contains some sample data. I've got an FE model here. Let me make this a little bit wider in my available data window. I have some sample time series data. This is some triaxial accelerometer data. So we do in fact have 3 channels of data that we're going to be looking at the frequency content and the cross spectra of those. And let me go ahead and open up this first process right here. It's called cross PST. And what I will do is take my time series data, drag it into this time series input glyph. It's going to be one of the inputs required. This particular glyph right here, this is just going to allow me to specify the number of bins in my frequency analysis. And we want to make sure that that's consistent across my PSDs as well as my cross spectras. And if I go ahead and maximize this particular glyph right here, it's a super glyph. You'll see that within it, it contains a frequency spectrum glyph here, and it also contains a frequency response analysis glyph here. Both of those will be generating the necessary plots in the frequency domain that we need to be able to perform a fatigue analysis on an FE model with multiple load PSDs. So let me go ahead and just hit the run button here. We'll take a quick look at the plots and then resume back into our PowerPoint presentation. So here we have the very first XY display. This is just showing us our PSDs in each of the 3 directions. We could use each one of these alone by itself if we were trying to do a single axis shaker table where we're looking at them sequentially. But because we've used this particular process, down below right here, we also have the cross spectrum and the phase of channel 1 versus 2. And I can index through some of these as well. We can see how channel 1 and 3 relate. And we have channels 2 and 1, channels 2 and 3, and then channels 3 and 1. So we have all of the cross spectra and the phase as well. All right, let's take a look at this next slide in the PowerPoint presentation. What we're looking at here is a screen capture of the load provider. And for any of you who've used the vibration fatigue glyph in the past, you'll notice that there are some changes. We have made this look a bit more like the graphical interface for the time series load provider. And the main reason for doing this is because when we get into multiple PSDs, the assignment of all of these PSDs, all of these plots in our different load cases becomes a little bit more complex. So we've decided to show this in a square matrix where on the diagonal we have our 3 PSDs. We have our X, our Y, and our Z directions. And then all the off diagonals are going to be the cross spectra and the phase plots that we generated earlier. The XML file, or that text file that gets generated, if I browse with this button right here, I can actually navigate directly to that particular text file that was automatically generated in the previous process, and it would automatically populate all the correct plots in this square matrix here. So you actually, as a user, are not required to drag and drop each individual one here. You can simply select that one file and it would auto-populate the matrix for you. So at this point, what I'd like to do is jump back into ENCODE and just give you a brief demo of the remainder of this vibration fatigue for multiple inputs. And to do that, I'm going to open up one more process. That is this one right here. It's already set up for me. And what I need to do is grab my FE results. If I show you just a few of the results in this particular results file, underneath this drop-down menu, under the properties, you'll see that for subcase 1, and that's the X direction, we have solutions in 10 Hertz increments, starting at 10 Hertz, and if I scroll down slowly here, you'll see that we go all the way up to 500 Hertz. We then start up with subcase 2, which is the Y direction, again 10 Hertz increments, and that would then be followed with subcase 3, which would be the Z direction. So we've got a solution for many frequencies in each of the three directions. If I go into the load provider, just to show you guys what this looks like, you can see that we have already populated this square matrix of all of our assignments. The browse button right here, if I click on that one, you can see this is that text file that would automatically build that matrix for me. It has however, already been selected, so there's really no need to define that one more time. And just to make sure that we have assigned a material to it, we'll take a look, and we have in fact just assigned a generic aluminum alloy to this particular bracket. So we are in fact ready to run it, and by clicking on the run button, we'll do a stress translation, and then count up cycles for all of the entities in my bracket, and then output some damage results. So this right here, if I enlarge the FE display glyph, we can now see a damage contour plot. And that same information is also being displayed in tabular format in this display glyph down here as well, in our data value display. We have in fact added some additional columns to the results that we can look at. Some of them might be a bit easier to look at in tabular format. But if I scroll a little to the right, we will notice right away that we have columns for all of our spectral moments. These are some of the numerical values used to determine the cyclic content with some of the counting methods. And we have a little bit further down here, life in the very last column. So quite a number of different statistical results that get outputted when doing vibration fatigue, because of the fact that the counting methods are assuming some type of a statistical distribution of cycle sizes. All right, let's go ahead and go back into the PowerPoint presentation, go to the next section. The next section is sign on random. And what we've really done here is introduced a new way in which we can describe the loading. And in this case, the loading is going to be some type of a random PSD. We can see that in red right here, overlaid with one or multiple sine tones. An example of this would be like the MIL Standard 810 handbook with a sign on random loading. We have a couple of assumptions that we should take into consideration when doing sign on random. The first one is that the stress response must be narrow band. And just to be clear, this isn't the load PSD, whether it's narrow band or broadband, but the actual local stress response on your structure. So if you're looking at a particular element, what is the stress response of that particular element in the frequency domain? Is it narrow band? If it is not narrow band, if it's broadband, and we're making a narrow band assumption, we tend to make very conservative damage estimates. So if it's not narrow band, at least it's going in the right direction in terms of a conservative solution. The second bullet item is that the sine frequencies must be completely within the noise frequencies. And this one is usually something that the controllers prevent you from doing anyway. So it's often not a problem. Third bullet item is that the sine to random power ratio must be smaller than 10. If not, again, we're going to start to see some conservative damage estimates. And then lastly, in the event that we have multiple sine tones, the sine frequencies should not be multiples of each other. So let's go ahead and go back into ENCODE. I'm going to navigate to a different directory to get some sample data for you guys. So let's go ahead and clear out my available data window and grab this particular directory here. And I have a sample process we can start with as well. All right, so in this particular process, what I'm going to do is grab my FE results. This again is a bracket, a little bit of a different bracket than what we saw in the previous example. I'm going to grab my PSD right here, drag it into this multi-column input glyph. This multi-column input glyph will be passing along the the random bit of my excitation or my load into the vibration generator, and we can go ahead and take a look in here. You can see here are the breakpoints from my multi-column input glyph. And if I go to this Advanced tab, you can see that we have described in metadata the sine tones that are to be overlaid. In this case, we only have one sine tone. It's going to be at 90 Hertz, and it has an amplitude of 0.2. So we will OK that, and if we just double-click on our glyph, go into material mapping, make sure that we have assigned a material to our structure. And we have. It has an aluminum alloy. That's good. We should be able to run the process. And there we go. We now have a damage contour plot. If I scroll a little bit to the right, we can see that we have predicted some damage results on this particular bracket based on random excitations with one sine tone. And in addition to that, we can look at some tabular results. And probably one of the newer columns in this one is the power ratio. So this is the power ratio of your sine tone to the random. And looking at some of these results and determining if that's less than 10 or not is going to tell you if you might expect some conservative results on a node-by-node basis. All right, so that is the sign-on random loading. Let's go ahead and go into the final section, which is modal superposition based on our frequency response function. So just to kind of graphically display what the inputs would be, if we're doing a fatigue analysis on a frequency response model prior to ENCODE 11, we needed to do a harmonic analysis in FE. And if you were doing this in Nastran, for example, you would have results in the form of an OP2 file representing your complex frequency response function. And we would bring this particular results file into Design Life, applying a PSD to that if we had random excitations, and then determining the damage as a result of that. This could be a very large model. A different way of doing this would be to do a modal analysis in FE. We could take the modal stresses, and then we could take the modal coordinates, which is going to be in the form of a PCH file, the combination of the two right here being much smaller in terms of disk space than this right here, but describing the same types of things, and then allowing Design Life to essentially build the frequency response function. So we're going to do this inside of Design Life. And the example that I'm going to show you in a bit, the size of these two files combined is 1/20th the size of this particular example right here with the original approach. Here you can see a table that describes the benefits of doing a modal-based frequency response function. If we looked at just one particular 2D element where we had 200 frequency steps and also 10 mode shapes, if we took the original approach, we have a real and an imaginary stress. Each one of those stresses has 3 tensors. And for the first approach, we have 200 frequency steps, which gives us 1,200 stress results per element in that FE results file. If we took a modal-based approach, again, we have 1 real and 1 imaginary stress component, 3 tensors each, but only 10 mode shapes, which gives us far fewer stress results per element that we need to address. And this is really what's going to allow us to dramatically reduce the file size of the FE results files, and also dramatically increase the computation time of the analysis itself. So let's take a look here at, let me go ahead and show you the process. And for this one, I'm actually going to, again, navigate to a different directory for some sample data. But what I will do is build this particular process from scratch, just so that you can see some of the properties that are required, some of the things that we need to change as we build this particular analysis. So what I'm going to do is grab my modal stresses. in the form of an OP2 file. I'm going to grab my PSD. This is in histogram format. And then my modal coordinates. So here's my PCH file. That actually needs to be dropped onto a modal coordinate input glyph. So let's bring that out onto the workspace. There we go. So the PCH file and the OP2 file, those are both coming from FE, representing my modal stresses and my modal coordinates. And this particular histogram file, that may be something that you had created earlier in ENCODE, or perhaps somebody has supplied with you. We're going to combine all of those into our vibration analysis glyph. So let me go ahead and attach some pipes here. And in this particular example, I'm going to make use of this red histogram pad for my PSD, and I'm going to make use of this multi-column pad for my modal coordinates. We'll get one more display out onto, looks like I can get two displays out onto this workspace for you. We'll have some FE display results there, and we can also graphically display the histogram, the PSD, and we could also display the modal coordinates if we were interested in looking at some of those. All right, so what I want to do, I'm going to go into something called Advanced Edit on the Vibration Analysis glyph. We will run the process up to this point. And now what I'm going to do is go down my tree structure over on the left and define some of the properties that are required to be able to do vibration fatigue based on the modal stresses. The first thing that we need to do is inside of FE results, this is the area that essentially allows us to interpret how we're going to process the FE results. I want to make sure that my entity data type is set to modal vibrations. This is the first thing that we need to ensure. That's going to allow us to grab those modal stresses. The next thing that we'll do is describe how the vibrations will be described. And we first need to go to this Advanced tab. This Advanced tab is going to allow us to describe modal loading. That's by default set to false, but if I set it to true, it enables a tab right here called modal. So now we can see that my modal set is available. I can select that one and move it to the right. And I can also take this piped in multi-column data, this is my PCH file, the modal coordinates, and assign it to my modal stresses. And by doing so, this is going to allow DesignLife to essentially build my frequency response function, which is going to be described in this tab here called FRF. I can now take that frequency response function that we're calculating, move that to the right, and I can drag my histogram on top of that. So here's my PSD, my random excitations described in histogram format. We need to go a little bit further down and make sure that we have a material assigned. So we'll just grab pretty standard material here. Let's try that one more time. There we go. And we should be ready to run our process. So I'm going to OK all of those changes to my properties, select the Run button, and we are now performing fatigue calculations. So here is our damage plot. Very simple model in this particular example, but you can see that we've got a little bit of damage occurring in the upper left end of our structure. If we look at the histogram in the first XY display glyph, perhaps we want to look at a log scale, and we can enlarge that. Here is the PSD in terms of G squared per hertz, going all the way up to 2000 hertz. And here are the first few of the modal coordinates. We're going to have a modal coordinate for each mode shape. And I believe we have 6 in this particular example, so we can set that to 6. So here are modal coordinates for the first, second, third, fourth, fifth, and sixth mode shapes with the real component. And there will also be 6 others for the imaginary component as well. So this information right here, combined with our modal stresses, is what allows us to essentially build that frequency response function in ENCODE. All right, let's go ahead and jump back into our PowerPoint and make our way through the end of this section here. So just to kind of recap on our modal-based frequency response function, we started with modal stresses and also the modal coordinates. Those were solved for in FE. We combined those in ENCODE. The modal coordinates, by the way, that particular glyph supports results from Abaqus, ANSYS, Nastran, and OptiStruct. And the big advantage here is that we are going to be dealing with much smaller files. In almost all cases, there are far fewer modes than we would typically have frequency steps, and that then translates into faster computation time. And there was the demo that we saw just a moment ago. So, in summary, what we've seen here is that we've had vibration fatigue capabilities in DesignLife for quite some time. It goes actually all the way back to version 4. But with version 11, which came out early this year, we introduced quite a few new features. The key ones being the ability to do multiple PSDs, as well as different types of loading, signed on random and signed well. We added the modal-based vibration fatigue, which allows us to greatly reduce file size of our results files and improve computation time. We've enhanced the static offset. Prior to ENCODE 11, the static offset was as it is, but now what we can do is actually scale that static offset. It might be nice if you have a linear response, for example, on some type of assembly load or preload, and maybe you have different levels of that load. You really only have to do one analysis in FE, and then we can take advantage of scale factors inside of ENCODE to manipulate that further. Isothermal fatigue is now a possibility with vibration fatigue, and we've also enhanced some of the stress combination methods. So with that, I would like to wrap up today's presentation. Thank you guys